Okay, hi everyone. Welcome to another BHI Colloquium. It's a pleasure to have Elias most here with us today. He obtained his PhD from the Goethe University in Frankfurt in 2020 and then moved to the IAS. He also won the Wheeler Fellowship at the Princess Center for Theoretical Sciences in 22. And he moved to Caltech in 23 and he's an assistant professor there now. Elias is a computational and theoretical astrophysicist interested in fundamental physics of compact objects, neutron stars, black holes. He's also told me he's working on the radiation belt in Jupiter. So he's a man of many interests. He's an expert on neutron star interiors, magnetospheres, numerical relativity, broadly speaking. So with that, I guess take it away.
All right. Thank you so much, and thanks everybody for coming. I thought today I'd tell you a little bit about accreting binary black holes, but also neutron stars. In particular, what can we learn from current ground-based gravitational wave detection, but also looking forward, what can we learn in the era of space-based mergers, where we have to care about all of the matter that happens around. I'll tell you some of the progress we actually made porting over insights from the EHT to binary systems. But before we get there, let me just quickly start out and also tell you about some of the people that done all this work that I will show you. That's the current composition of the group. You recognize some of the faces throughout the talk, but I just want to give an opportunity to show everybody, since not everybody will appear in the talk itself. And so what I will be talking about then is really sort of gravitational wave events. So what happens when two black holes collide or when two neutron stars collide. I'm part of the Simulating Extreme Spacetimes collaboration. A large part of the work is really focused on producing accurate predictions for LIGO-Virgo events, where the idea is if you have merging black holes with spins, precession, nowadays also eccentricity, what kind of prediction can we make for direct comparison with data? I'm somewhat in a different camp in the collaboration, thinking more in terms of what happens if you have stuff around the black holes, or if you have neutron stars involved, in terms of what kind of multi-messenger prediction can we make. And so what I will do is, for me, these systems look a bit different. For example, this is a neutron star black hole merger. And I'll tell you a little bit more about how those work. I'll tell you about the microphysics we can learn in the system, and also what kind of physics techniques we use from other communities, from high energy or nuclear physics, to really model some of the dynamics that's going on there. This is largely for sources that are being observed at the moment. There's the ongoing observation run by the LIGO-Virgo-Kaga collaborations called O4, will last until October. There will be a short shutdown period. But going from that, one of the really prime targets for this is sort of all of this merger of neutron stars, black holes, and associated transients. And then as we go forward, the things we have to think about, kind of the same physics in terms of GR, but really very different physics in terms of matter around them. What happens when we go to space? There's currently ongoing observations with the pulsar timing arrays in terms of trying to get a gravitational wave background for the most massive mergers in the galaxy, which is 10 to the 9 solar mass orbiting galaxies. And maybe there's some hope, especially with future facilities led by Caltech. I'll show you DSA 2000 later on in this talk, to detect individual events, maybe over the next 10 years. But then also next decade, you'll see in 2035, space-based gravitational wave detection with LISA will actually enable us to get a feeling for what the merger of massive black holes between 10 to the 5 and 10 to the 6 solar mass will look like. What I will show you in the second part of the talk is how we can use kind of the same technology that we've developed for the stellar mass black hole case and port that over also using some insights from the EHT. Okay, before I begin this talk, giving you some more insights into what we've actually done, I want to give you kind of both a warning and some encouragement. So this talk will really be more on the simulation side. So for me, all of this will be done largely in pictures. So we use large computer simulations, but they come with caveats. And the caveats you can already see in this painting here. This artist paints sort of this kind of gamma ray burst origin model. The idea will be, there will be assumptions we bake in, there will be some choice of colors, some choice of painting styles, and then only I think by comparing multiple of them do we actually learn something. That's really the approach that we'll be taking in this talk. Okay, so without further ado, what do we actually have to solve? Just, I know many people here work on black holes, but I'll also briefly talk about neutron stars. And there the physics is similar, but some aspects are a bit different. So if you want to model a neutron star collision, you really have to account for kind of similar physics. There's general relativity involved, but we really have to go to the dynamical regime. So we dynamically solve Einstein's equations to not only get gravitational wave signals, but also, for example, to account for the formation of a black hole, because this system can be gravitationally unstable, collapse, and then we can track that on a computer. And so if you want to model more than a black hole, you also have to model the matter itself. For this, we solve equations of hydrodynamics. But in principle, that's not enough. because hydrodynamics doesn't really tell you what the fluid composition is. So we need some nuclear physics input, which for us really comes from largely phenomenological models that extend all the way up to the PQCD scale. And then that may even not be enough, because if you want to predict electromagnetic transients, or even if you want to understand what the secular evolution of the system is, how long does it live before it forms a black hole, you need to account for Maxwell's equations. They're really, really critical in terms of angular momentum transport. So that we have to solve as well. And then that's another complication, which is unique to the neutron star case. Since you have all of the neutrons, they have weak decays. It's really, really important also for electromagnetic afterglows. And so we need some form of weak interactions and neutrino transport as well. And putting all of this together in a blender, this is what I'm going to show you the first half of the talk. Okay. And so this is kind of a prototypical simulation of a neutron star merger with my former grad student in Frankfurt, Cosima Boy, just to get you kind of a feeling for what that looks like. And so here what this is solving is Einstein's equations plus hydrodynamics. You can see all the two neutron stars orbiting. What you can't see in the background is gravitational waves carrying out angular momentum and energy from the system, but you get some idea that the stars come ever closer together. And so ultimately they will collide. And just if you have a collision, there's a little debris that will fly out, which you can kind of see here is this kind of smoky rendering that comes out of the screen. This is very neutron-rich material. Those neutrons will undergo rapid decays. By our process, they form heavy elements, they decay, they power an afterglow. I talked a bit about this. And then ultimately here, as you can see, gravitational waves carry out further angular momentum, you form a black hole, you dynamically collapse, and then now you're in the regime where all of the technology also used for GRMHD simulations for supermassive black hole accretion comes into play, because the system can launch a jet, large parts of the disk, 30 to 40% can become unbound, and it can power transients.
So yeah. What are those colors?
The colors are the rest mass density. So they basically logarithmically color the number of baryons in the system.
It's mostly neutrons, or it's all sorts of things?
So the interesting thing is, so the neutron star is actually not mostly only neutrons. It depends on how deep you go in. And that's largely set by weak equilibrium. So at the surface, you have roughly similar number of neutrons to protons. As you go in, you get to 10% neutrons, and then it depends on your symmetry energy. So what happens around saturation, whether you go up in protons again or not. And then at the center, we don't even know what's in there.
You need to know, well, that's partly an answer to my question. Do you need to know the equation of state all the way in, or how much do you need to know?
Yeah. So for really understanding the merger itself, roughly those systems probe densities of about 4 to 5 times saturation. So we need to make an assumption. And one of the things I'll show that in a bit for future generation detectors is more like end of the 2030s or so, is actually to get a better handle on what the equation of state looks like, because they're imprints in gravitational waves. And so that's one of the main motivations.
A question from the chat. What is the remnant in these models, black hole or neutron?
It depends very strongly on the initial masses that you start out with. So basically the neutron stars, even with spin, have a maximum limit, right? So you cannot go beyond the Keplerian breakup spin. And so when you add them together, you form a certain mass. And if it's too heavy, they will immediately collapse. This is a case where you get a stable lived remnant, but on the shortish side. But I think for the event that we have seen, 1708-17, lifetime is about hundreds of milliseconds. Yeah. But that's a good question. Okay, and so what I want to very briefly do for this system is I want to summarize some of the points that were already asked, which is great. And then after that, I'll show you some of the more recent work that we've done in this context, which will bring us slowly over to the realm of black holes. Okay, so the main idea is we've seen a few events involving neutron stars already. We'd love to see more, but so far we've seen one very big event, 1708-17. There was a multi-messenger event. I'll show you some of the multi-messengers in a second. We've also seen some black hole neutron star mergers, which are very, very interesting, as I will show you, because they can power interesting new types of transients powered by the black hole itself. And of course, we've seen many, many merging black holes over here. So all the blue dots are black holes, the orange dots are neutron stars, and then the half dots is neutron star black hole. And then we already had that question in terms of what kind of nuclear physics do you probe? So far, what we can see from the events that have been detected, because the detector is only sensitive in a regime below 1,000 Hertz, that means that we're sensitive largely to this inspiral part of the gravitational wave signal. And that probes densities around saturation and a little bit less. But from this one event, you learn a lot, because what you probe is effectively neutron star squishiness. So the neutron star is very big, it's more squishy under tidal process, and you can put an upper limit on neutron star radius and then translate that over into constraints on the equation of state. And the nice thing is, as we'll see more of them, especially also with future generation detectors like Cosmic Explorer, we're actually going to get a very, very tight handle on the equation of state in this regime. And then, of course, if you want to know at higher densities, you really have to think of this system as a cosmic collider, which you can. And we've actually done, I won't show this today, but Kamas asked me later. We've done direct comparisons between gold-gold collisions for low luminosity heavy ion events, collision events. This is more for the FAIR facility in Germany that's currently being built. And there you can do a direct comparison of what you would see if you had a neutron star collision versus a heavy ion collision. It's very, very interesting because gravity changes the entire picture, but the physics that are probed at the collision itself, at the point of contact, those are the same. Anyway, so there's more physics that's going on there, but I won't really talk too much about this in this talk because that's something for which we would need future detectors, because that's all the part of the signal that's between 2 and 3 kilohertz, and that will take a while before we can detect this, but we're optimistic. Okay, the other thing that brings us a bit closer to the black hole aspects is all of the multi-messenger parts that come with this, because if you have this matter around, if you eject it, you can power afterglows, and we've seen this. In fact, several of my colleagues at Caltech were one of the first people to observe the 1708-17 event. And there's 2 types of transients. One I will talk a bit more about, the other one I will not cover extensively today. One is the afterglow itself. This is because you have all of these neutrons and they recombine into heavy elements. They produce a lot of metastable elements in the way, in the process, and these decays power a transient that peaks about 1 day after and then fades away. This is something that people are very actively looking forward for if there's a new event that's coming up. And then there's another thing for which we have much more data, but less association with gravitational waves directly, and this is short gamma ray bursts. The 1708-17 event clearly established that there was a short gamma ray burst about 2 seconds after the merger. So those are one of the primary engine models. And our questions are, how many of them can source short gamma ray bursts, can source, some of them also source long gamma ray bursts, so a very peculiar part of long gamma ray bursts. And a lot of work in the community that we'll show you today has been devoted in clarifying this up. So the nice thing is here for 1708-17, you had a time delay of 2 seconds. You get a very nice observation radio that was done at Caltech. Also, the afterglow observation was done at Caltech by Mansi Kasdibal. So there's a lot of interesting things that are happening, which is good for us because on the physics side, on the modeling side, there's always a lot to do. And one of the things I think that I learned from accretion physics, and where I think there's a lot of interesting things going on also in the solar context, is really the generation of magnetic fields themselves. Because if you want to power any electromagnetic transient, you need sufficiently strong fields to both affect the dynamics and to really get matter ejected in the first place. And if you just think about your typical pulsar observations, your neutron stars have magnetic field strength of 10 to the 8 to 10 to the 12. If you do a quick back of the envelope estimate, the magnetic fields that you need to change the dynamics in a neutron star, like equipartition field, that's 10 to the 18 Gauss. So there's no way that if you just take the magnetic field of a neutron star would matter at all. So there's something going on, just like it's going on in the sun with its 11-year solar cycle, where you convert some of the kinetic energy in the system into the magnetic field, you drive amplification, and then by what's called the dynamo process, really get a strong magnetic field that changes the entire picture. This will be one of the things I'll focus on in this talk. Okay? And so simulations have so far shown that if you start up with weak field, you get amplification during the merger itself, and that can go up to more than 10 to the 16 Gauss, where it's dynamically important. And in particular, we made a lot of progress in understanding how then the field breaks out of the star, and what does that tell us about potential counterparts. So this is some of the things that you can do today with modern computer simulations, using numerical relativity, using GR-MHD, and now we're even building more subgrid physics and to better understand what's actually happening if you were to connect this ultimately with the neutrino viscous scale, where most of your dynamo folding would happen. Okay, and then the big question for the system, which goes into one of the questions that was asked earlier, do we actually know, let's say if we see a short gamma ray burst, if this was really driven by a black hole? Is it a typical black hole jet type system, as you actually see nicely in the painting just behind the room? Or could you also have a magnetically driven wind that would come from the star itself? There's certain questions or points for and against either. So this one, for sure, we know can power short gamma ray bursts. But one of the important questions is the neutron star itself can, via magnetically driven wind, also power an outflow, principal Lorentz factor 10 to 20. The big question now is this sufficient? Does it explain part of the population or not? And one of the things where numerical relativity comes in is to actually make predictions for this. There was a recent finding of quasi-periodic oscillations by NASA scientists in archival GRB data, sort of indicating that there might be some oscillations going on, which they associated with oscillations of the hypermassive neutron star, just if you do a frequency matching. So there is some motivation, also observation, to think about this scenario. And so what we in the community did over the past 2 years was actually figuring out how to do this. which is very, very interesting. And there are at least some connections to the solar dynamo problems. And so first of all, there were simulations by, which you can see by Gottlieb, basically showing that the black hole disk engine system is very, very slow. The main reason is that there most of the magnetic field amplification happens by the MRI, and that takes a certain time to ramp up. If you look at the timescales in most cases, they may just not be sufficient to explain things like seconds delay. It might just take much longer. At the same time, we figured out, really from the magnetic field dynamics inside the hypermassive neutron star that you formed in the movie, how the magnetic field can get amplified, can break out of the star, and then launch a strong relativistic outflow. There were several works by different groups independently that found the same thing, which is really, really interesting. And then we doing a lot of work in terms of understanding this and modeling that effect. And I want to show you,
Can I ask
yeah.
a quick question?
Uh-huh.
I'm trying to understand these two models, and neutron stars have such high magnetic fields.
Mhm.
And if they form a black hole, I'm trying to understand, where does the magnetic field go?
So that's a good question. A student of mine is currently simulating that. So what can happen is, so what's different from those neutron stars, the common ones you see from like pulsar observations, the magnetic field is even stronger. So the amplification, this is what those simulations show, can go up to more than 10 to the 16 Gauss at the surface. There's a really, really strong magnetic field. Now, if you put the magnetic flux on the black hole, what can happen is if the flux is strong enough, you can form a transient jet that goes out, which is just entirely powered by the flux you accreted on the black hole. It's not sustained by accretion, and so you basically get some sort of GRB precursor that you could get, which then has to shut off until the magnetic field in the disk can take over and provide enough flux. So there might be another transient state that you can form. And now what we're doing is, showing this later in the talk, we're using some new subgrid model that we developed for dynamo action in these systems to kind of systematically probe this and match out the parameter space. That's a very good question. There may be observational angles of this. All right. Now, what I want to show you now is just sort of to get some idea of what is kind of the main insight that those simulations have actually shown. This is the thing that we weren't able to capture before, but we understand better now. This is really how do you get a kind of all of this turbulent mess that the system will form into producing a coherent large-scale field. And there's some very nice analogy to what happens at the surface of the sun. So basically, just like the sun, the neutron star remnant that you form is a differentially rotating profile. It's going to be uniformly spinning at the core. There's an outer Keplerian envelope where you go to the disk, and then it has this intermediate profile over here. And so what will happen is, if you do have magnetic field action amplifying your field over in this region, just like in the sun, you can have field lines that buckle out of the star, sort of magnetobuoyantly go up by means of a Parker instability, which you can see here. There's a full numerical relativity simulation, by the way. So there's everything included, but we do something to the magnetic field. The field then buckles out. You can nicely see so this connected loop. Then it will explode away, will get ejected, just like in a coronal mass ejection event in the sun, opening up the field lines. And if you do this a few times, you end up with a lot of open flux, and you can drive an outflow and a wind from the star. So you kind of figured out the in situ jet launching mechanism for the system, so to speak. There are questions in terms of neutrino physics, because if you have a very strongly neutrino-driven wind from the star, you can pollute this region, and that may ultimately get your Lorentz factor down. Or you follow up work looking into this as well. And this works actually quite similar if you think into the magnetar flares, where you also kind of launch the field. The difference is here, the field action is really driven from what happens inside the star, rather than just some crustal activity. Okay, and then ultimately what we showed is basically what I just said. So you get these individual flares, you propagate further out, and then you form what's called a magnetic tower, which you can see here, the nicely helical structure that develops. So you really kind of self-consistently launch this outflow. And there are previous models for this, going back for like earlier GRB models, as well as there's also models for white dwarf mergers, which should in principle do the same thing. Just the follow-up physics would be different in terms of a different light curve and breakout from those flares of the surrounding ejector. Okay. So now that we figured out that neutron star merger remnants get these extreme fields, and we are thinking about what happens if the field comes to the black hole, why don't we actually ask the question more generically? What happens if you have the strong field, you put it on the black hole during collapse, is there any kind of transient that we would expect? There's been a lot of work for this. In principle, there was a very nice analysis being done by Vikram Ravi already 10 years ago, like what's the maximum lifetime of a neutron star remnant, quite phenomenologically, but in principle, some of them, a very small fraction, less than 10%, could live up to a day. Depends very strongly on how angular momentum transport in the star lives. And if that works out, then basically what will happen is that your magnetic field, which is on the star, can form kind of a nice outer dipolar shape, which then will have to get ejected, or something will have to happen once you put that on the black hole. So the big old problem, basically, what happens during collapse, where you form a black hole with your magnetic hair. Similar things also happen with scalar hair, by the way. If you go to modified theories of gravity, we did something on that too. But the main thing that we did now that's new about
So,
this, yeah,
Elias,
go ahead.
how can it be a day when the dynamical
Mhm.
time is so much
Mhm.
shorter?
So the interesting thing is there's kind of a phase diagram of angular momentum transport in a neutron star merger remnant. Some of them collapse through accretion-induced collapse, just from the accretion flow. Some of them can basically live for a while as a uniformly rotating star, and then spin down would trigger.
Okay, so the day is just when it collapses,
When it collapses. This is
but
all
the
about
escape of the field is still on a dynamical
yes,
time?
exactly. That's on a dynamic time. I'll show you and do that in a
Okay,
second.
fine.
That will happen in a millisecond.
Fine, I thought you said that will be a day.
No. Just a lifetime of the system. The main reason we have to make that assumption is because I want to basically show what happens if you have already a well-defined exterior field. If you go in earlier, you still have the accretion disk around, you still have this turbulent field, you have the split monopole type geometry of the field. But that will do something different. So I'm here basically going to a case where the entire accretion disk has largely been ejected or accreted, and I basically just have a very, very strong magnetar sitting in space. And then I can ask a cleaner problem in terms of what happens if I form the black hole. It's a good question. And then yeah.
Hypermassive means
Mhm.
between 1 and 2 maximum neutron star masses.
So hypermassive basically means, so we know, for example, that the mass to collapse, direct collapse at the merger is 1.6 times maximum non-rotating neutron star mass. Hypermassive is roughly above 1.25. It's a bit equation of state dependent, but roughly in that regime. Basically, what I'm saying is that the terminology is a bit loosely used, but I'm saying that whatever comes out of the merger at the end is not long-lived. Which here even I count a day as not long. And then one of the interesting questions you can ask even observationally, you should take this with a big grain of salt, because those associations, both for an FRB to GW 190425, that was like a merger where you wouldn't expect a necessary, or you wouldn't expect a long-lived remnant, you would expect prompt collapse, or this Rowlandson paper where there's a problem with the association. Either way, both of them basically claimed you could associate an FRB, or in this case, an FRB GRB to a single system or a single source. And that sort of raises the interesting prospect of maybe this even has some observational implication where you have a time delay between what happens at merger, and then you might get another transient at collapse itself. And so what we did in this work is we kind of revisited this problem, and that's an old problem that has been studied for quite a while. The difference, what we had now, was a much better understanding of the physics, the plasma physics in the magnetosphere of this neutron star. In particular, what we understand is, this was kind of the picture most people have. This is nice dipole radiation. This is what happens if you collapse something in vacuum. The magnetic field will just go out. You could basically use that for a nice textbook problem on what that would look like. But that's not really reality. It's not really a transient that would look like that. Rather, what would happen is that the waves that come out will non-linearly steepen. There's nonlinear dynamics in the magnetosphere of the neutron star, and then they might form, or we show they will form, what is one of the strongest shocks in the universe. It goes by the name of monster shock. And it works pretty much like this wave here that you can see. There's a nonlinear steepening in a way that some points move faster than the points at the base. And then if you're a surfer, you get sucked in, and exactly the same thing happens here as well. We did the first simulation showing that that's actually the case. And so what you find, this is kind of the outcome of the simulation. I'm showing you Lorentz factor and temperature. Those are 3 different snapshots. So here you still have a star at the center. There it's almost collapsed, and there you just have a black hole. And you can see that as the star begins to contract, it launches a sound wave, much like I'm speaking. It launches a sound wave, but it's called a magnetosonic fast wave that's going out. It's subject to the same steepening as the wave as it comes ashore for effectively the same reason. For the wave, it's because the bottom of the ocean changes height. Here, it's because the magnetic field decays. So it's something almost like slow roll inflation. You basically convert energy from the wave into acceleration of the wave itself, but the wave is limited. It cannot go beyond the speed of light. And so something has to happen, and this is where you begin to dissipate, which you can see there in the temperature. And so we see that we formed a shock, which has been analytically predicted by Andrei Balaborodov just a little while ago. And the interesting thing is the shock is only limited to the background magnetization. So in reality, background magnetization of the system is like 10 to the 8. So you would get Lorentz factor 10 to the 8 of the system, which is extreme. So you would in situ pair create and then produce a massive fireball that isotropically goes out. And our simulation shows that exactly this simulation, which situation with this negative ingoing velocity, just like the surfer that you see in the wave, is reproduced. And so this system actually produces this monster shock solution pretty much accurately, which would predict that some of these mergers would be accompanied by something like a very, very short gamma ray burst, on the order of a few milliseconds at the dynamical time scale. Okay, and then you can basically look here more at the wave geometry. One interesting thing about this is this does not just work for collapsing neutron star systems. It also works for neutron star black hole mergers, which is something that we have primarily observed within LIGO. But one thing I want to mention before we go there, which I think is interesting also, is not just that you only see the sort of shock itself, but one other thing that we found, which I found pretty exciting, is that the black hole, when it initially forms, is not a stationary solution. It's ringing, just like a bell is ringing when it's perturbed. And we can see that the ringing of the bell is not just imprinted in the gravitational waves that's emitted, it's also imprinted in the electromagnetic waves. So this here is showing the electric field. And you can basically see this regular spacing. Those are ring down modes of the black hole itself. So if you would see a gamma ray transient, it would have a quasi-periodic tail. And the quasi-periodic tail would exactly correspond to the oscillation modes of the black hole. So you can maybe even use them to probe gravity. So my feeling is, by the way, what Cecilia saw in those observations might be more this and not the hypermassive remnant. Anyway, I think this is interesting. And so we thought, okay, this is not the only situation where this would happen. In fact, LIGO got very, very unlucky in the sense that most neutron star black hole mergers are such that the black hole, the neutron star gets swallowed whole at merger, meaning all of the transients that we've seen initially, afterglow and GRB, they can't happen because there's no material behind. But because you can form these monster shock type solutions, and this also has an exterior field just by construction, you might just be able to produce a transient at merger itself. And so what we did was the first simulation, so the full MHD magnetospheric simulation of a neutron star black hole merger, where the neutron star is swallowed whole, and we're able to show exactly that the same thing happens. So we produce a monster shock. So this is, by the way, what this looks like if you've never seen this. A full numerical activity, the neutron star gets sucked in, the black hole just slurps it up, and then it's gone. Okay, and so once the field has transitioned onwards, you can look at the same kind of shock structure. We identified monster shock formation the same way. Just that's because in this system, you'll not end up with a magnetite that's merging, but at lower field strength, the prediction is actually you should produce a fast radio burst from this by a shock-powered maser emission. And so we found kind of a new mechanism to produce FRBs from neutron star black hole mergers.
Did you say shock-powered maser?
That's right. That's right. This is one of the models that people use for FRB emission, right? That you have sort of this.
It's like a synchrotron maser?
There's a synchrotron maser, that's right. That happens when you collide basically this outgoing wave with the electron-positron outflow.
And if you were to show magnetic fields on those that upper triptych,
Yeah.
what would they look like? Because, I mean, because you've got a huge magnetic field on the neutron star. Did that get slurped up?
That gets slurped up. So you basically it gets slurped up, and then because it gets slurped up, you sort of pull on one end. It's a very asymmetric process, right? So the magnetic field is here. You pull it in this direction, which means you give it a radial perturbation, and you launch this very strong monster shock in the same way as in the collapse.
So that's mediated by the field.
That's mediated by the field, exactly.
Before it disappears.
Well, the field is still around, right? So this is basically asking the question, the field goes on the black hole, and then somehow the field has to dissipate. I'll show in the next slide how it dissipates, which is interesting in itself, because it also does something very unusual. But here it's more the question, while it's getting swallowed, you really, really strongly pull on this field, and as a result, you launch a wave in the field. Well, it's not really an alpha wave. It doesn't propagate along the field. It propagates perpendicular to the field. And then it produces this ultra strong shock, which will give you a transient. It's like a whip that you swing, and then you hear basically at the end, when the point at the end gets infinite speed, you hear like a bang. That's the same thing for the magnetic field. And now the big question is what happens with the field after this transient, because it has to go away. And so we also have an answer for that, because the simulation revealed what actually happens is you form a black hole pulsar, which was very unexpected too. So what will happen is the field goes on the black hole, but the field retains angular momentum. And so it's basically like a black hole with a magnetic field that's just spinning around. But the field is still shed, so this is a transient, right? The field cannot live very long because the black hole no-hair theorem is still valid. But you can, at least for less than about a second or so, have this black hole, which produces the same kind of striped pulsar wind that a pulsar has. You still have this transient and can produce gamma and X-ray via reconnection in the wind. So at least for a second, it looks like a pulsar, almost, without an inner close. So I think this is very, very interesting. And so in that sense, even those black hole neutron star mergers, which you would think would be totally boring because they leave no matter behind, are so interesting dynamics that in principle, they can produce FRBs, they can produce gamma rays, and they can also produce an X-ray transit, just for when the striped wind propagates out and then ultimately reconnects all that energy.
So there's enough matter left after the slurping?
It doesn't need any matter because it's only mediated by the electrons and positrons of the magnetosphere. So all the neutrons are gone, but all the leptons are still around. And it's the leptons who do the job. So this is how you get around the case that all of the neutron star is swallowed, because the exterior part of the magnetic field does not go into the black hole. It's only the star itself that goes there. And then we basically see how the very strong field that's still left around has dynamics that can convert some of this energy into an observable transient. We basically figured out the way this works.
Elias, I have a
Yep.
quick question.
Sure.
What is the relationship of the magnitude of this field compared to that on the neutron stars? I think I missed the color coding.
It goes down by a factor of 100.
100, I see. Okay.
But it's still quite enough to power an X-ray and gamma ray transient just from reconnection to striped wind. This is what you see in some of the pulsars.
And can you predict the time scale, or is that coming?
Yeah,
For
the time scale of this event, so the lifetime is roughly 1 second. The challenge is a bit that the field decays exponentially, and so we did a back of the envelope model for reconnection, the striped wind, which kind of predicts that the overall time scale of what should come out should be of the order of 10 to 30 milliseconds. That would be the time scale of the transient roughly. Just by getting an estimate, basically how long it takes for the wind to A, dissipate that energy, and B, how long the field is still strong enough, because it's still decaying exponentially, right? The thing doesn't want to have hair, so it's still getting rid of that.
Yeah, that's
Hard to catch it.
detectable, right? With the pulsar, millisecond pulsar.
So this would not be in radio. This would be in gamma ray and X-ray. But the good
Oh,
thing
gamma
is
rays. Okay, sorry.
you could catch it. So there's a postdoc now at Caltech, Aaron Tovavu, who has implemented a new continuous commanding strategy that you can use on X-ray and gamma ray satellites. It's already in production, where basically if they get a LIGO trigger, the nice thing is, I mean, here you would get a gravitational wave trigger. So if you get that early enough, like a few minutes before, they can start slewing the satellite and they have an optimal search strategy. So they may actually be able to reposition the field of view fast enough to maybe catch something, but that's TBD. That's already implemented, so we'll know as soon as something happens. Yeah, that's a very good question. And speaking more about this sort of search for precursor emission, this is what this is called. This is because the transit would happen at merger, something we haven't seen yet, but people are looking for. There's also hopes to see something in radio. So my colleagues at the Owens Valley Radio Observatory are also looking for this, largely with the long wavelength array. One of the challenges is it's only in the sensitivity about 100 megahertz or so, which is a bit more of a challenge, just in terms of the predictions that we make. But it's very interesting because they have all sky coverage. And so what they demonstrated is, in principle, that some of the gravitational wave event would come in, and they would know it would roughly be in this region. They are now able to store very, very high time cadence data. In the past, they had a 10-second binning, which was not good enough for this. But now they have improved the sensitivity by a factor of 100 as of like last week or so, that they're actually able to store enough data once the trigger comes in for up to 1 hour, and then search for, was there any transient in radio that accompanied? And for that, you need all sky coverage. Otherwise, it's very, very hard to see where the merger happened, because you don't know that at the time of merging. And then DSA 2000, this new radio telescope, which also will devote some of its time to gravitational wave follow-ups, will also have something like this commanding strategy, where they will also try to slew the detector into the right position. And CHIME is doing a similar kind of analysis, trying to see if you find a GRB-FRB correlation. There, of course, it's much, much harder. Because they only have like 10 candidates, and they're kind of assuming maybe there's like a 10-year delay or so. If you assume that the magnetar formed and the merger lived very long, and then maybe produce something. But so far, that search has been inconclusive. Okay, another thing that we do for this, we also make a lot of predictions in terms of those flares, what kind of FRB transients they can do. This is one of the ones that we made. I don't want to talk too much more about this. Black holes can do this too. But one of the interesting parts about radio is not just that we can do predictions for radio, but also that we can make predictions for things that have already been observed. One of the ones, if you go to gravitational wave conferences, that always come up is the question about precursors to long gamma ray bursts. Also, some short gamma ray bursts have these precursors, which basically, if you look at this prototypical one, there's a main burst, and then shortly before merger, there's sort of smaller burst that precedes it. And some of the models that have been put forward for this is basically maybe there's some resonant shattering of the neutron star crust mediated by gravitational tidal forces that then ultimately cause the crust to shatter, so transient to propagate out. And then the claim was maybe that's enough energy to do gamma rays. There's no questions about this if you look at the nuclear physics of how much energy you can actually store in the crust to power something. But that's one of the potential mechanisms with the cartoons that have been put forward. By the way, if you think, oh, this just looks like a nice egg that you're cracking, I think the picture you should have in mind is more like this one, right? It's more like a doomsday for the neutron star before they collide. Anyway, the thing that we did just last year was to say, all right, you can do that, but ultimately the question is, can you actually predict what type of emission you would see? Is it just okay, the thing cracks and then somehow gamma rays come out, or can we do better? And so we utilized large-scale GPU computing to actually simulate the process of what happens if you launch what's called an alpha wave from the surface of a neutron star. The idea is, by the way, very old. It goes back to Blandford and Goldreich and Omar Blaze in the 80s. This is what this looks like. If you have a neutron star and a black hole, you have this kind of massive earthquake doomsday event. And then you propagate out these waves along the magnetic field lines. And we could equally show in the study that A, you're very likely to produce a shock power transient. So you would likely get an FRB, not a GRB from this. But you also get some secondary X-ray through reconnection in the magnetosphere over here. So that would happen as well. And so then the big question is basically we can use kind of all of this technology to make predictions for all of these sources and hope for our observer colleagues to ultimately pick up on this and maybe hopefully observe something.
Are the colors there again density?
The colors, no, the colors here is magnetic field. This is basically supposed to show you that there's a wave going on. So blue and red is just showing you effectively the amplitude of the field of the wave. And so you can see that this wave is propagating out. And then here you can kind of see there's some transition happening, which is discontinuous. This is where you form a current sheet where you're dissipating in the magnetosphere where you have signs of opposite polarity. But this largely happens because the wave is forcing. So there's some forced reconnection going on in the binary magnetosphere. Okay. All right. And so one thing I want to very briefly mention is one of the big challenges that we have in simulating all of this, much like if you simulate black hole accretion flows, the microphysics can get quite complicated and the scale separation is quite daunting. If you think in terms of the typical neutron star merger, you have kind of a jet scale covering, which actually can be much larger than 1,000 kilometers that you have to bridge. Orbital separation is okay. That's something we have to resolve if we want to capture gravitational waves. But all the microphysics that we need, which for those dynamo processes would be at the neutrino viscous scale, that happens on sub-centimeter scale. So even if you make the back of the envelope estimate 10 to the -6 of micrometers, there's no way you can put that into a single simulation, just because the scale separation is far too large. But maybe you don't have to. Maybe you can do kind of a subgrid approach, where you would just as for reconnection say, okay, maybe I'm in this one parameter range and I put model A, or I'm in this different parameter range, I put model B. And so the question is, how do we do this in a way that's consistent with physics, but also that we can use in any of this numerical modeling? And we've worked, and we actually are currently working on several of those models in the way of putting in dynamo physics, putting in dissipation scale effects, and so on. The way you have to do this is quite interesting. You have to use approaches kind of pioneered by different communities. For example, a lot of the reconnection physics that you also just see in the neutron star case was actually initially driven by space physics, because you can send spacecraft missions there. This is like Mercury, and you're interacting with the solar wind. If you send a probe through, you actually get information. Prashant was saying we're also involved in some of the Jupiter radiation belt analysis for the Juno satellite, which is a bit different. It's less about reconnection physics in that case, more about the fusion in the magnetosphere. But here, the other thing is, this is, of course, all non-relativistic. So we need a relativistic modeling of those processes. And the only community who has pushed this, because they were data-driven, was the heavy ion collision community. Because they have actually 360-degree observations of collisions. And when they kind of reconstructed their momentum space, they found what in plasma physics you would call a Scoot-Maxwellian distribution. So they have observational evidence that what you would call GRMHD in an accretion flow is not sufficient. So they developed a lot of technology to be used in that context. And so what we're doing at the moment, kind of a longer term effort to port over all that knowledge and put that into the astrophysical context, where basically you have to interpolate physically between something that looks like kinetic theory and something that's hydrodynamics. And the way you usually do that in physics is perturbatively. Okay, you start out from one end, and then you want to add in systematic corrections that kind of account here in this cartoon for changes in your mean free path. And so the way you do this is you kind of use reductions of the kinetic equations of the Vlasov equation in our case, and then try to bake them in or make the coefficients match the physics that you want to model. One thing that we showed in the past was you can do this for MHD, so we can do all kinds of dissipative transport, which is for viscosity. Now we actually also have resistivity. I'm going to say one word about this on the next slide, for heat conduction and so on. So we can basically model them in a way that's consistent with relativistic fluids, including anisotropic transport and so on. Just want to briefly mention that. And of course, the latest thing we did on that was also to make this compatible for these alpha omega dynamo models. To give you some idea, this simulation by Kenta Kiyuchi is the most expensive simulation ever done for neutron star merger. That thing cost, I asked him, about 500 million core hours. It's a 4,000 cubed simulation with everything. The problem is you can't run that on a regular scale. I think it took him 2 years to run in the first place, right? But the physics that's going on that he found for all the money that he spent is very, very simple. It's very basic dynamo theory that people worked out in the 60s. The question is, maybe we don't have to spend that much money. Maybe we can just, cook it up in equations and just calibrate to that simulation, which is what we did.
Is this
last year.
basically saying Blanford's Nyack is probably right?
So this is not Blanford's Nyack. This is more like, we have a simulation showing this is more like Blanford Payne in a sense, because you can also get a brief Blanford Payne period. But here the main thing is more what basically, this is not a black hole, it's a neutron star. It's more about the alpha omega dynamo. There was also recent work where people claimed that part of the sun should have a similar effect, by Daniel Lecoine and others. Anyway, but it's more in this direction. And the easy thing is, because what Kenta found in his simulation was, it's the easiest thing you can think about. It's the alpha omega dynamo coming from MRI. We can model that effectively. I think even Ramesh did this for black hole accretion flows about 10 years ago. Just have a more general formulation that also works in 3 dimensions. And then the other thing that we're doing at the moment is we've extended this formalism to include resistivity, not just on the equation side, which we worked out a while ago, but also on the numeric side, which will allow us to get better reconnection physics into those black hole accretion simulations. In particular, the main challenge was A, figuring out how to solve the equations correctly, and B, getting them on GPUs, because it was quite slow in terms of the initial debugging. But I can talk to you more about this if you're interested after that. Okay. Any questions on the neutron star side? If not, in the final sort of 10 minutes, I'm going to show you how you can apply all of those things to merging black holes, doing exactly the same thing. And so here, the motivation is actually a simulation we did very recently. I talk more about that simulation in detail. What you can see is that the magnetic field dynamics are quite complicated. In fact, in the simulation, we propose a new accretion state, which resembles the mad accretion state for a single black hole, just showing that also works if you have 2. So the main motivation observationally is there's pulsar timing searches with nanograph going on at the moment, also the International Pulsar Timing Array collaboration, where you want to understand what actually makes binary black holes merge, because it's quite unclear what actually drives them once you get down to parsec scale separation to sub-parsec scale separation. So gravitational wave emission is rather inefficient, and so you need some other dissipation channel. Typically what people say, it's either dark matter or it's gas. And so one of the challenges with gas is how exactly does that work? So what's the accretion dynamics of a binary? And especially what's the accretion dynamics if you have strong magnetic field? And the motivation we had for that was that one of my colleagues does cosmological simulations, and those simulations seem to indicate that you can form this actually, okay, it's not a cosmological simulation, it's more like a collapsing gas cloud, and you get subsequent mergers. But what you find is in those simulations, you form a binary inside a hypermagnetized accretion disk. So you have an accretion disk where the magnetic field is so strong, it kind of keeps the stability of the disk. I'll show you some example later. And the question then is, okay, if that happens, maybe these binaries will merge differently than what you would think if you just had typical viscous accretion on a binary. And that's the thing that we look for. The other motivation is if you have strong magnetic fields, they may also completely change the electromagnetic counterparts that we expect to see with LISA in about 10 years when it's going to launch, where you'll see the merger of 10 to the 5, 10 to the 6 solar mass black holes. So the question is, can we just use all the technology we have to make a better prediction? And so you've never heard about this problem. I hadn't myself until like half a year ago. So the current state in that community is roughly like this. It's actually something that's also been pushed at the CFA a lot by former grad student Magda Zivek. So the idea is basically you have an instability here. You have these 2 binaries that orbit, so you exert a gravitational tidal potential on this outer accretion disk. There's a competition between viscous forces and tidal forces, and then you get an instability at the inner limb resonance where you open up this cavity. So that's entirely gravitation, right? So things just going around, and unless your viscosity is not too high, you're going to clear up this cavity, and then you get the stream accretion. So far, so good. There's been a lot of work that's been done in the community over the past 10 plus years, where people using 2D simulations, because they need orbital integration times of like more than 1,000 orbits, have figured out roughly what the mass ranges and eccentricity ranges are for this system to spiral inwards. Because if you accrete too much angular momentum, they actually found, especially Munoz and Lai initially found, that they might go outwards, so that accretion may not help make them merge, rather may make it worse. And so there's a very narrow range of parameters that would make them in spiral. And so the question is, okay, is this generic? Is this something you would just believe based on those simulations, or is there something missing, given all the work we've seen before neutron star mergers, but even more so, given what we've seen in Event Horizon Telescope observations or in the accretion disk community? Because this is just 2D using an alpha viscosity. It's basically assuming everything is thin and it's nicely flowing inwards. And we know by much work that has been done actually here that maybe that's not always the case for how black holes accrete, especially with very strong magnetic fields on the horizon of the black hole, which I leave that up to you to tell me if this is indicative of the mat state or not, the polarization image. But if you take that as an indication, then the accretion dynamics would be very, very different. You would basically get magnetic flux eruptions that transport angular momentum in this outer accretion disk. And so the idea that you just have like a nice smooth flow that's going in may not be applicable. So the question is, if you do this for the binary, does that work? Does that not work? And does it really change the picture? And so what we did was we basically used a lot of computational time to get some initial insight into that, because the community before had really not considered this problem because it's very, very expensive. So if you look at what had been done before, most of the community focused on sort of a regime where either you cut out all of the inner binary dynamics, there's no way that you get magnetic field feedback by construction of those simulations, or they did this in numerical relativity where all you can do is 10 orbits. But we know from physical timescales in the system, you need hundreds of orbits even to get in a proper inflow equilibrium states. It's something you couldn't even see before. And so the way we did this was we used the new GPU-based code on more than 1,000 GPUs, and we just cranked the problem through to more than 200 orbits for strong magnetic fields in the initial condition. Just the same thing you would do for your single accretion simulation in a EHT type black hole, right? And so if you do that, we found, I can already take this away, that the same mat state that you found for a single black hole also works for two black holes, but slightly differently. So what we found in detail is this. This is two black holes. This is the outer accretion flow. And now we just keep this going. This is what everybody has been seeing if you I can only integrate for like 8 orbits. And then even after 50 orbits, so this is density, it's showing the gas density as it's going on to the black holes here. It kind of forms these mini disks. Everything looks the same. And then suddenly, as you integrate it beyond 100 orbits, there's a change in the accretion flow itself. You can see that there are outflows, much like jets being launched from the excision spheres. There's some ordered thing going on in the cavity, like it looks less turbulent. And if I show you the plasma beta parameter, which shows basically where the magnetic field is relevant, so gold is where the magnetic field is 1,000 times stronger than the fluid, you basically, in this entire cavity, establish an ordered magnetic field geometry, the same thing you would see in a mat, just on a much, much bigger scale, encompassing both of these excision spheres. Okay, and so basically what we found is that if you start with strong magnetic fields in the initial condition, which can be about beta 10 to the -2 or so, you quickly go into a case where this binary is encompassed by very strong magnetic fields and resembles something like a mat state, to which none of the previous analysis in the literature is applicable.
Elias?
Yeah.
So these are really two individual MAD systems?
No, this acts as a whole mat system. So the way you should, I will show.
Okay, how should I think about this?
I will
I'm a little
show you.
bit lost.
Yeah.
Is the background dynamical in that case because you were.
So the background, so this, okay, so I should say, so there's two things here. First of all, there's a Newtonian simulation because GR is not important for what I'm showing. The other thing is the background is dynamical. So those are two spheres on a Keplerian orbit and they just go around 200 times. Okay. So that's very important. So that's in there because otherwise we wouldn't get the tidal forces on the accretion field, like this cavity.
Back reacting, it doesn't back react.
Oh no, here, but it's not expected to back react on those numbers of orbits. It's expected to back react on a much longer time scale. Here we just want to know what is the steady state sort of accretion state. What would that do if I were to instantaneously compute the angular momentum transfer on the binary? And so I will answer Ramesh's question in the next slide. But what I want to show first is what this looks like because that may already help. So we find that each individual black hole or sink has its own sort of tower-like outflow. So we have individual jets. So each of the sinks would be mad. They were real black holes. But then what's different is that you get a lot of reconnected flux, and that just fills up this cavity.
Yeah.
So that's what basically happens. And then you just have, it's more like a young stellar object, right? Just that the field is not anchored in. So you basically have a lot of net vertical flux that just sticks around, but is so strong that the accretion onto this black hole itself, so the accretion on this scale, behaves like a mat. There's an interchange in stability, there are flux eruptions, all of that. Just the difference is you don't need the black hole, you just need the fact that you have a cavity, which by the way also means that the mat is more general than in the black hole case itself. And then we can do the comparison right over here. So this is kind of a 2D rendering where you see the individual field lines. This is not cutting through the black holes, just to basically show you what the cavity background dynamics look like. There's also flares that are being produced, but I can talk about that later. The main thing is you have flux eruptions in the same way that you have this in a mat, right? So you have this region which gets ejected outwards and then transport angular momentum, just like in the regular mat case. And we also have a comparison here with a typical GRMHD simulation of the process, and they look basically identical on that scale. Okay, and we also see like the presence of Rayleigh-Taylor figures. So even all the emission physics will carry over, with the caveat that the field strength are a bit different. But the same processes will happen as well. And then the main thing that we were initially interested in was, would that actually change the orbital dynamics? Because Ramesh had a very nice paper with Caltech, who was a former fellow here, analyzing angular momentum transport in the disk. And you can do the very same thing for the binary as well. You can see here in pink, this is the magnetic field mediated angular momentum transfer. And the flux tube transports from the binary. Yeah.
Look what I'm doing.
I love the monitor.
Yeah,
Okay.
it's good.
So
like
transport
yes.
angular momentum outward from the binary. And the interesting question then is, does the system shrink with accretion or not? And we picked the system where all the 2D results predicted it should expand outwards and never shrink, which is shown here by this red line. So this is a quantity which gives you the angular momentum transported per specific accretion.
I just feel bad.
So anyway, this doesn't matter.
So many good students.
Above the red line,
You're just kind of like,
if it's below the
oh, you.
cyan line, it would
I was
decrease.
like,
And you
yeah,
can see
this
once
is
you
a
enter
great
the
amount
average,
you get for the
you're
like,
much lower than where 2D hydro
Oh my
makes
God,
a
there's-
prediction, meaning that this will actually change the orbital evolution of the system if you can maintain it.
There are so many.
So read the mat state changes also
Interesting.
for two
enthusiastic
black.
people.
if
Yeah.
it's a-
You're doing a 3D.
Yeah, and like for
Yeah,
a lot
full
of the people with
3D,
the
full
like,
3D.
that they're
That
not
had
like
always
knocked it
been
out of the park.
question.
but,
Just
like-
going to 3D, what will it do?
That's
But
right.
now you're saying it's probably the magnetic field that's the big deal.
That's right. That's right. So even I talked with Julian Krolik, I mean, they had also done 3D simulations for fewer number of orbits and not the mat state, more like a sane flow. In the sane flow, the rate also goes down, but not as low as for the
Not
mat
as
state.
much, okay.
So really the mat state seems to change the picture quite a lot. Yeah, that's right. And then the other thing I want to very briefly talk about is that, you know, this is kind of a toy problem that we did. Just because it's so expensive, we can only afford to run a few of them. But one thing that we need to think about is really in those realistic environments, the thermodynamics may be very different. So this is a simulation done by one of my grad students, Haiyang Wang, where we change the thermodynamics in the disk, basically the cooling. That changes whether in the other case was strongly cooled, this one is not cooled. Then you form like more of a puffy region, you still get flux eruptions, but that regime may be more closely what you expect on galactic scales. And I'll show you why. Because one work we have in preparation is to actually figure out what is a more realistic initial condition for the system. So we teamed up with Minghao Guo at Princeton, who's done these zoom-in simulations, which I know some people here have done as well. But this time we did them for an M87-like potential, but for a binary at the center, just to see sort of what is actually the state that you form. And you form this accretion disk. So this accretion that starts from, I think the outer scale of the box is like 60 kiloparsec. You use 20 refinement levels to go all the way inward. And then what you find is you form this accretion disk on scales of 5 parsec, which is exactly the scale that you are interested in for like most systems, but that's chosen by the potential in the background. So that's by construction. But then the interesting thing is that now here you have the two black holes. I had to mark them because it's very hard to see since the accretion disk we form is warped relative to the binary orbit. We have some more renderings I can show later where you have a jet going out from each of the black holes. The jet is intermittent because it will hit the warp disk at some point. But basically we find very, very similar morphology, just with the difference that the cooling physics, which here we approximate with the combination of Bremse and line cooling, is much more complicated. So you end up basically with a hot sort of bubble at the center on orbital scales and a very cold hypermagnetized accretion disk around. And so now we're figuring out if the same kind of approach that we did for the MAD binaries also applies to more realistic initial conditions. And the next thing, it turns out with Phil Hopkins here, of using some of his initial simulations as initial condition, because he has more realistic initial conditions for this problem. Anyway, so I think we already kind of showed that really some of the insights gained for a single black hole accretion carry over, and they really tell us the system might be more complicated than what you could imagine. The other thing that we asked was, okay, if you want to use that for LISA, one thing you have to think about, does the flux actually stick around by the time of merger? It could be that you accreted, and then it just gets lost all the way before the black holes emerge. And so in this simulation, what we did is we used the previous simulation as an initial condition, and then we ran the system all the way to merger, where we basically just put like a simple post-Newtonian orbit prescription. And you can kind of see the line of black holes here larger separated, and then they kind of head towards merger here. And the scales we talk about is that this cavity size is about 100 Arg initially. And what's interesting is that while the orbital dynamics is still coupled to the disk, you see these massive flux eruptions. And then as expected, the binaries sort of head to merger much quicker than the accretion flow can keep up. And so they decouple, but still you have accretion to Rayleigh-Taylor fingers, which is very characteristic of the strongly magnetized regime, which otherwise you also wouldn't have. And that has very strong implications if you ask questions such as, do you have X-ray variability? Like one of the telltale signs that has been proposed for the system was that you had X-ray emission that would shut off because it decouples. But it's not so clear if now you have the Rayleigh-Taylor accretion. Just stick around. And then the other thing that you can ask in this case is, okay, if you take this, you put it on a GRMHD simulation, what would actually happen? And so some work done with Sean Ressler actually simulated what Bondi accretion now in GRMHD onto two orbiting black holes will look like if they head towards merger. Question is, if you launch jets and they interact, maybe you get some non-thermal emission. The interesting part was he basically picked some parameters, which I will admit by chance happen to look exactly like what we simulated on larger scales. So I was very happy in the sense that we now have a prediction for what the merger in the sort of strongly magnetized cavity with large net vertical flux would look like in full GRMHD. And so what you find, very briefly, you find dual jets that are being launched. This is the magnetization. So you see the two jets. Depending on what the spin precession of the system is, they can be misaligned. So the jets can cross. You get non-thermal emission from jet crossing, which you can see here. You find nice reconnection zones. You can make predictions for emission from that, which largely would be in the MEV band, but you have to be a bit careful of the conditions there. But then ultimately, what also is nice is all the things I told you about these flares that you see in neutron stars, which could produce precursors to gravitational wave events. Black hole can do that too, if they create large coherent flux. So everything we've seen before carries over also to merging black hole in the same way, given that we can basically produce a precursor emission there. And even something else will carry over, which will be the last thing I'm going to show you today. And that has to do with flares in Sagittarius A star, where you have certain models where you think that the flux eruptions in the mat state could power them. Well, guess what? So here in this case of the orbiting binaries in this huge vertical flux, the flux is only stabilized because you have a tidal potential from the binary. Once they merge and that's gone, you sit up with a huge amount of flux that's no longer force balanced and will basically explode outwards. And so you get a ginormous flux eruption after merger, which you can see here, where if you plug in the conditions for synchrotron emission in this regime, resemble roughly what you found in single black hole accretion for Sagittarius A star, with the difference, of course, that the parameters are a bit different. You have to be a bit more careful what the field strength out there are. You're kind of suppressed basically by the separation, but then the scaling in this vertical cavity is different from a regular fall-off, so that saves you basically a factor 10. Anyway, if you run the numbers, you still end up roughly in the near infrared regime as an order of magnitude estimate. Yeah.
Can you go back 2 slides?
Yep.
Maybe? So you said when you have these two jets, they each form, sorry, these two black holes, each form, one more slide forward.
Yeah.
Yeah, this one. So each black hole forms its own jet.
That's right.
And in this lower right panel, is that supposed to show how the two jets merge?
It's flux-tube coalescence.
So
They basically do this.
the jets wind like a braid.
Uh-huh.
And then that happens before the black holes merge.
That happens before the black holes merge. That's right.
I see. So by the time the black holes merge, there's already one jet.
By the time the black holes merge, the jet will, in this scenario, briefly shut off. And then it will resume because all the flux that you have on the cavity goes on the black hole. Same question as with the collapsing neutron star. You bring all the flux in, and then you'll immediately launch a jet from that.
So this braiding structure dies, and then something else.
That's right.
comes in?
But the braiding structure, the reconnection, as these two flux tubes collide, can produce non-thermal emission itself. And that's interesting because most of the predictions done for these LISA counterparts focus on thermal emission from the accretion disks. But if this is active, then you will also see non-thermal emission from the jets themselves, which will be much more prominent if you have this mat regime than if you don't have this mat regime, just because you have enough supply of magnetic flux.
Is it just for supermassive black holes?
That's for supermassive black holes. That's for.
Would you expect this for the kind of LIGO events?
I think the interesting thing would be there's some models for LIGO events in AGN disks. So there's some models for that. We actually have, I don't think I have time, but I have one more thing I could show where we actually looked into this. We have like a black hole traveling to the disk itself. I have observer colleagues who are looking for this actively for LIGO events. There's some follow-up with ZTF, that's why. There's one claimed event that was done in 2019. It's not clear this is really associated with this, but there are models where basically either you get emission, but once the black hole breaks out of the disk, or you just change your line emission because you have all the energy injection from the jet into the AGN disk itself.
It's like a QPE or something where.
No, for the QPE, I think the leading model is more that you have a TDE that forms a disk first, and then you have a star code. That's the leading model for the QPEs that like Itai Lineal and Brian Metzger pushed. over the past year or two. Okay, if there's no more questions immediately, I can stop it. I can stop it here very tall. Yeah.
I guess if you have one burning question. Yeah.
I mean, there's just too much here. I can ask lots, but the way, right at the end, you talked about post-merge.
Yeah,
There'll be one kind of a giant hiccup, right?
that's right. That's
One
right.
big
One very
flux-
big giant
flux
hiccup. Yeah,
eruption.
that's right.
So how much energy is going to come out of that for the observer, that is?
Yeah, that's the thing that we're still trying to estimate. I think the biggest question is that we don't have a good handle on yet. What is the required magnetic field strength that you really need? I think here I would think for this system where we assume that we have very large fields of up to 100 Gauss at the horizon, should be basically similar estimates for Sagittarius A star.
Yeah,
It should be like it's not well, the distance is larger, so that may not really help. But I think it's good that at least carries over. And now what I hope is that from the cosmological simulations, we get a better handle for what we actually start with initially. And then I think we can match that.
Right. I mean, so you got the energy scale for the photons, but I want to know actual ergs. How many ergs are going to come out of this hiccup?
Yeah, I think one thing that we estimated was if you just take the full black hole, the close separation here, and you would dissipate all of that, that could in like a very short time, that could go up to 10 to the 42-ish or so. But that's on the very extreme side of things.
Okay.
Right. So that's the upper limit. I mean, and the crazy thing is you just have so much flux because this thing goes all the way up to 100 RG. Right. So the big question is just what you start with. When you start with this, you go to the regime of 10 to 40. The question is just, I think realistically, we should aim for a bit lower. Yeah.
Do I understand correctly? You're saying that the final parsec problem would be solved by magnetic fields?
I'm saying that magnetic fields will play a role in this for sure.
Okay. So they're not like, you're saying we could check this off, like this is.
I wouldn't check it off yet. I mean, there's also, I think I talked with people in nanograph who are currently trying to see if eventually you could also place some constraints on dark matter just by the slope that you have in your orbital decay. There's a correction to the typical Peters formula that you use there. My feeling personally is, I mean, this will for sure be relevant forward towards merger. The big question we have to figure out is how much coherent flux you can get on this parsec type scale, which really goes back to this cosmological initial condition. Because there it seems that the cooling from the ISM physics changes a little bit of what the dynamics close to the black hole is. So I will not want to make a strong statement right now, but I think it's promising. That's what I can say.
Okay, let's thank Elias again for this. So Elias is around for today and tomorrow. He'll be sitting in this office right here, 209. So you can even catch him there.